Hey guys, welcome to 2019 Level 2 Ways paper for Level 2 Physics. So question 1, satellite dishes. Satellite communications can help isolated communities stay in touch, as well as improve signals for television and radio communications. A typical receiver dish, shown below, can be used for a range of waves in the electromagnetic spectrum. The receiver dish can be modeled using a concave mirror and light rays. Although a satellite dish is not truly concave, a teacher decides to model the image formation using a concave mirror. Complete the ray diagram to show how parallel rays are reflected in concave mirrors in general. So as seen in the diagram, the rays are traveling parallel to the principal axis, which means that the rays will reflect back through the focal point. So each three of these waves are all parallel to the principal axis, which means they're all going to reflect back through the focal point. So starting with the uppermost ray is going to hit the mirror and it's going to reflect right through the focal point, just like that. The second ray is also going to reflect back through the focal point. Should look something like this. And the lowermost ray should also follow the same rule. So all three rays should reflect back through the focal point. So should look roughly like this. All three waves going through the focal point, and this should be an achieved question. Okay, I'm not. As I was saying in some of my previous videos, I do not have the marking schedule for this test paper, and that does mean I do not know which question is merit, achieved, or excellence. But I will use an estimated grading criteria, so I'll just estimate each question's grades based on past year papers. Alright, so B. The students realized that in order to use the mirror for the model, they will need to know its focal length. They placed a 3 cm high Lego toy 30 cm in front of the mirror and determined its image to be 2 cm high. By first determining the distance of the image from the mirror, calculate the focal length. Okay, so first thing you want to do is you want to write down all the variables that the question will give you. So they tell you that they placed a 3 cm high Lego toy. So that means that assuming that the Lego toy is the object, then our height of our object is told to be 3 centimeters. We are also told that the Lego toy is placed 30 centimeters in front of the mirror. That means the distance from the object to the mirror will be 30 centimeters because the toy is 30 centimeters in front of the mirror. So we also know that the distance of our object to the mirror will be 30 centimeters. We're also told one more information, which is the image is 2 centimeters high. So we're told that the height of the image is equal to 2 centimeters. And then we're asked to find the distance of the image from the mirror, so that's di, and also the focal length, and that's f, okay? So basically we need to find di, and we need to find our focal point. Alright, so first things first, we want to find a relationship that we can use for these three variables given to find one of the variables we do not know. So the question does give you a hint here. So it's like by first determining the distance of the image from the mirror, calculate the focal length. So it gives you the hint that you have to find di first. So you can use the relationship of hi over ho is equal to di over do. So hi over ho is 2 over 3. And that is equal to di, we do not know, over 30. So now we can use cross multiplication. So we say 2 times 30 is equal to 3 di, so cross multiplication here. So we can say that 60 equals to 3 di. And if we move the 3 to the other side, we can find that our di is equal to 20 centimeters. Okay, so now we can use our relationship between the focal point and di and do. So we can say that 1 over f is equal to 1 over do plus 1 over di. So therefore 1 over f is equal to 1 over 30 plus 1 over 20. And this should simplify. Do need a calculator here. So 1 over f equals to 1 over 30 plus 1 over 20. Or don't have a 600 over 20 plus 30 over 600 equal to 1 over f. So therefore, 600 over 50 is equal to f. So our focal point should come out to be 12 centimeters. And that should be your final answer for this question. And this question should just be a merit level question. In terms of getting an achieved grade, so if you get up to DI equals to 20 centimeters, then you should be able to get an achieved grade. Alright, moving along. CI. Draw two rays from the logo toy to locate the position of the image. You have to draw and label the image. Okay. So for this question, we have to use our rays, the laws between concave mirrors and rays in order to locate our image. So the two rays that I find is the easiest to use is a ray that's traveling perpendicular to the principal axis, and one mirror that hits that goes directly through the principal axis. Alright, so first ray I find the easiest. I mean, there's so many different rays you can do, but the ones I find easiest would be a ray traveling perpendicular to the principal axis. So it should look something like this. Yeah, it might not look very good because it's on a digital iPad, but traveling perpendicular, not parallel. So a ray traveling parallel to the principal axis, when it hits the pole of the mirror, it's going to reflect back through the focal point. So that's reflects through the focal point. And our second ray that goes directly through this, the principal axis is going to follow the laws of reflection. So the angle of incidence equals to the angle of reflection. So should look roughly like this. Yeah, once again, I don't have a ruler with me, so I can't do everything perfect, but the image should look roughly something like this. So just a rough image of the object. No, what am I doing? Should look something like this. So the image is formed when the two rays meet, which is right somewhere right here. Yeah, sorry. This should be the image and the object should be straight, not bent, but this iPad isn't going to do much for me, is it? Yeah, sorry. It should look something like this, and the ray should start from the principal axis and come down to a point where the two rays meet. So unfortunately, I can't get quite accuracy on the iPad, but on paper, you should be using a ruler and making sure that everything is roughly accurate. So it says to label the image, so you can just say that this will be your image. Alright, so this should just be this by itself should just be an achieved. Okay, so what would be the effect on the position of the image of increasing the radius of curvature of the image? Alright, so we know that our focal point is equal to two times of our center of curvature. Actually, no, it's the other way around. Yeah, so two times our focal point is equal to our center of curvature. We can say it's our C. So if we increase our radius of curvature, then that means our focal point will also increase. So basically, this question can be reworded. So we can just reword this question. And we can just say, instead of this, we can just say, what would be the effect of increasing the focal point? Which will make this question a lot more straightforward. You can just say, explain your answer, so you say 2f is equal to c, therefore as c increases, focal point increases. And then you can link your focal point increasing to the location of the image. So first things first, in CI, you can see that when the toy is outside the center of curvature, So it's really far outside. That's going to be producing an diminished, inverted, and real image. However, as this focal point increases, the position of the focal point increases, then when the Lego toy is on the focal point, then you do know that there's actually no image formed. So if I just draw a quick sketch somewhere, so if we have, for example, here, so let's say we have our object here, and let's say this is also our focal point. So oops, oh gosh. Okay, so what happens when the object is on the focal point is actually these two rays here, they're actually parallel, which means that they will never meet. So it doesn't matter which way I extend them, I can extend them back, but they're never going to meet because they're actually two parallel rays if the object is on the focal point. So you can say that when the object is on the focal point, you can say real rays nor virtual rays meet. You can say hence no image. And you can also link it to when the object is inside the focal point. So if I draw another quick sketch somewhere, find a good place. I'll just draw another quick sketch. So if we have our axis and our object is inside the focal point. So let's say this is our focal point, then this should look like something like this. So as seen, when the object is inside the focal point, then it will actually create an enlarged virtual and upright image. So that's important to note. So you can say when the object is inside. It's inside the focal point. It's inside the focal point and an enlarged virtual and upright image is formed. And that should be your final answer for this question, and this should be a meritable question, I'm thinking. However, it could be excellence as well. Depends. Alright, D. The students replace the mirror with a concave lens. They place a Lego toy in front of the lens as below. Complete the ray diagram to show the image produced and describe the nature of the image formed. So we have our concave lens. So this is the exact opposite of a convex lens. So we're going to be applying our rules for our concave lens. Alright, so a ray traveling parallel to the principal axis is going to hit the lens and it's going to experience some refraction. So the ray is going to bend. So the ray will bend, and the rule for this and the rule for a concave lens for ray traveling parallel to the principal axis is that it will refract away from the focal point, but it will be it's hard to explain, but it will be on the focal point, but it's going to refract away from it. So it might be a bit easier if I show you straight away. So basically, the rays are diverging. Basically, that's what I'm trying to say. So basically, if I extend this ray back, then it should hit the focal point. Yeah. So it should look something like this. And we can also use our rule that the ray traveling through the principal axis will go through undeviated, which means that the ray will not change position. So basically, the ray traveling directly through the principal axis will go through undeviated. So go through like this. So basically, as you can see, the two real rays, they're diverging, they will never meet, so they're going to get further and further away from each other. However, if we extend them back, we can find our virtual image. So if we extend them back, we can find our virtual image when they overlap. Very, very small image, so it should be here. And that will be our image. Alright, so the question wants us to state describe the nature of the image form. So basically, you just need to our three orientations. So if is it upright or inverted, enlarged or diminished, or real or virtual. So as you can see, this image is a lot smaller than the object, so it's going to be diminished. And it's going to be upright. And it's going to be a virtual image. Alright, thank you for, this question. Okay, so what I'm thinking here is that possibly, I'm thinking this is a merit question. However, if you get both, if you get CI and CII, both CI and CII, you can get a combined excellence grade for those two questions. However, I think D by itself is just a merit question. However, I'm not sure on that one. Otherwise, this will be an excellence question, and I don't think this is an excellence question. Yeah, I'm not too sure. Yeah, but yeah. Thank you for watching this video for question 1 of the 2019 Waves walkthrough. In the next video, I'll be posting question 2 and question 3, so stay tuned for that one. Thank you, bye.